So we want to continue our applications of integration, but we want to expand it to polar equations, right? So we're going to add in the area of a surface of revolution. So if we have the area of a surface of a revolution of a polar curve, it's defined two ways. So you have your function f continuous on alpha to beta for theta, right? So theta is between alpha and beta. The area of the surface formed by revolving that graph from on that region and about the indicated line is as follows. Now I'm not going to derive these. I'm just going to tell you what they are and you use them. So if you're deriving around the polar axis, which of course is the positive x-axis that we know and love. So the polar axis would be revolving it around this piece. So if you're revolving around that piece, or quite frankly the other side of it, that would be this formula right here. So 2 pi from alpha to beta, f of theta, sine theta, and then that looks like arc length. That's, or because it is, right? You're taking the arc length and then you're multiplying it by the function value and then the sine in order to get the area of that surface of revolution. Okay? And then to get that surface area, if you're going around the other axis, so the theta equals pi over 2 axis, which would be this one, but also its companion kind of down on the bottom. There you go. That's this one. All right, so when using this formula, check to see if the graph of r equals f of theta is only traced once. In other words, yet again, we need to have only one period, traced only once. So you can not have more than one period. That's why that period finding method in Desmos is so important. Because you'll need it for your limits of integration. All right, so let's see here. Find the area of the surface formed by revolving the circle r equals f of theta. Okay, so that circle is right here. You can see the circle. And I'm going to take it and I'm going to imagine it spinning around this axis or this line, theta equals pi over 2. So you're going to spin it around. It's going to form kind of a donut shape, although the hole won't really be there. So it's, I think, called a torus. Yes, indeed. A torus is a fancy name for a donut. So you can see the spindle torus is kind of what we're looking at. So one where it kind of touches inside, or perhaps a horn torus, something along those lines, right? So it doesn't have quite the ring that a donut does because it doesn't have that hole in the center. Okay, so that's, now we've imagined it. We need to know what the period of this graph is, because if we don't know the period, then we won't be able to do this. So let me go to my graph. That was my Zoom recordings from my class. All right, so I need to figure out what a period is for this graph. So if I start at 0, I'm over there on the far right. And then if I swing it through, all right, so that's pi over 2, so pi. Looks like the period is pi. Matter of fact, the period is definitely pi. All right, so we'll make a note. The period is 0 to pi, to out a full circle, or a full circuit of this circle. Alrighty then. So surface area, by definition, is going to be, since we're going around the theta equals pi over 2 lane, we're doing the bottom formula. So it's 2 pi, all right, alpha to beta, but we just figured that out. Alpha and beta will be 0 and pi, right? So 0 to pi, f of theta, cosine of theta, square root f of theta squared plus f prime of theta squared d theta. Well, there's a mouthful. Okay, so, and heck, I mean, if I want to keep consistent with the formula, I'll call this alpha and call this beta. Okay, so let's leave myself some space because I got a lot to write here. So this is 2 pi integral. Alpha is 0, beta is pi. F of theta is right here. It's cosine of theta. So that would be cosine of theta times the cosine of theta, square root cosine of theta squared plus derivative of cosine is negative sine of theta squared d theta. Oh, this isn't going to be that easy or hard a problem at all, because this is 2 pi. That's cosine squared. And this is this cosine squared of theta. Oh my goodness. Almost didn't have an angle. My pre-calculus teacher just got mad at me. So it's the square root of cosine squared theta plus sine squared theta, because of course when you take a negative and you square it, it turns it positive. But this is 1 by the Pythagorean identity. And the square root of 1 is 1. So there's nothing to worry about there. So this is equal to 2 pi integral 0 pi cosine squared theta. And we've seen that formula before. It's in our giant integral table of doom. Let's bring it back in here. Come here, integral table. There it is. Cosine squared of u du is 1/2 u plus sine u cosine u. It's formula number 52. It's right here. All right, so let me kind of move that over so I can see it and write it at the same time. So let's see here. This is equal to 2 pi. I'm going to write the formula I'm using, of course. Number 52. So it's 2 pi times 1/2 theta plus sine of theta cosine of theta from 0 to pi. I'll make that disappear now. All right, because u for me is theta. I mean, it's really easy. There's no even u substitution in this problem. All right, the 1/2 and the 2 are going to kind of cancel, so we don't have to worry about those, right? So they are out. So that leaves me pi times, and then I'm going to put pi in here, and I'll put 0 in here. So it's pi plus sine of pi cosine of pi minus 0 plus sine of 0 cosine of 0. Okay, well, the sine of pi is 0, so that's gone. 0 is 0, and the sine of 0 is also 0. So all of that is 0. That leaves me pi times pi, which is pi squared. And of course, it would have millimeters squared because we're finding surface area. Surface area is area, so it's squared. Now, if I want to verify it really quickly, okay, so 1, I can find out what pi squared is, if I could type it correctly. There you go, so that's no problem. And then I can take the 2 pi times the integral, and then I would take it from 0 to pi. I'm actually going to type in the full original problem. So it's cosine of x. Well, I'll just take cosine of square root of x. Let's not get too excited. Right, cosine of x times cosine of x is cosine squared of x times the square root of cosine squared of x I don't really need that part, plus sine squared of x. And then I have to go out here, close that parentheses, and then dx. Ta-da! It's pi squared. It worked out. So I can verify with my Desmos that my integral that I originally set up is equal to, in fact, my answer that I came up with, which is always nice.